All right. So, here's what we covered. Right, so before I solve a problem, let's just do like a little bit of a step back and see what the topics are, like the big topics. We had 5 classes worth of stuff, and so we had these fundamental kinematic relations. This is really the ones where you can think of where we take the derivative or we integrate, right? So that's the that kind of problem. A projectile motion problem, that's just a specific kind of scenario of a constant acceleration problem, right? So that's these are problems. We have relative motion problems. We have constrained motion problems. So we always think of those as pulley problems. We have rectangular coordinates and doing kinematics in rectangular coordinates. We have coordinate transformation, we have path coordinates, and we have polar coordinates. So those are the things that we've covered. So you can think of the problems that you want to prepare for kind of fit into these different categories. So you want to be on the lookout for those as we're preparing and as you're testing yourself. Here's on the equation sheet, this is the section of the equation sheet that we'll be using, right? And everything that you really need is right here. Don't need much more. It's just all the other equations are just variations of this. So these were a bunch of different projectile motion problems that I had included on there. We can't go through any of those if you wanted to. But is this the one that you wanted to do? Is this the first problem that you were referring to, Osama? Okay, let's take a look at it. This is the Angry Birds problem. So what we have here is we know this. We want to find the initial velocity, right? So we have a point in space. So they're showing this little star right here, and we know that it's starting 10 feet up off the ground, 20 feet away from the location we want to go to, which is 8 feet off the ground. So we want to, and we know that the launch angle is 30 degrees. So we need to know what the initial velocity is. And we're told what the answer is going to be, which is kind of nice of us, don't you think? When we get started here. Getting my cheat sheet out. Boom. All right. So really good idea to list out the things that we know in the problem, right? Make a even though that we might have the sketch of the thing, I think it's worth, kind of like think about it ourselves and kind of making a little picture of the thing. And there's where we want to get to. Here's where we started. This was like 10 feet, and this was 8 feet. We got 20 feet away. Here's that angle, which is 30 degrees, and we're going to find VO. All right, so we might say that we're going to choose XO to equal 0. We'll try as YO is equal to 10 feet. The eventual X that we want to get to is 20 feet away, and the eventual spot we want to land is 8 feet up. So the equations that we're going to want to use, we want to have X is equal to X naught plus VO X T, and Y is equal to YO plus V naught Y T minus 1/2 GT squared. Come on, focus. There you go. Come on. Something might jump out at us that we want. Let's go ahead and try to reduce this down a little bit by saying that we know that VOX is equal to VO times the cosine of theta, and VOY is equal to VO sine of theta. We want eventually only want to get VO anyway, so we need to get rid of those. One thing that we don't know here is we don't know time. So we kind of want to try to get rid of that. That's like our strategy. That's our thought process. The thing we want to remember in projectile motion problems is we have two independent, almost independent motions, one in the vertical, one in the horizontal. The only thing they have in common is they're happening at the same time. So they're linked together by time. So we'll go ahead and just solve for time here. I'm going to go ahead and just get rid of that XO because we know we're going to start at 0. So we could just say that it's going to be X divided by VO cosine of theta. And we could put this guy back into this equation right there. I don't have enough desk space here. I don't know why that is. So we get y is equal to y naught plus VO sine of theta. We're going to replace that time with this right here, so that becomes X divided by VO cosine of theta minus 1/2 G. And by the way, we're using feet, right? So we can know that G is going to be 32.2. We'll replace that in a second. We want T squared, so we're going to have to square this X. VO gets squared too, and cosine gets squared. Got to remember to square that. So we see that the VOs cancel out. We could even make this turn into tangent of theta. That's useful. And we have a lot of this information, right? So from our original thing here, we go, well, y is going to be 8 feet. Y naught is going to be 10 feet. Now we have tangent of 30. X is going to be 20 feet minus 1/2 32.2. X is 20 feet squared divided by VO, which is what we're looking to get, and then the cosine squared of 30 degrees. So I can work all of this out, all of these values here, right, and bring out VO over to the side, right? So I can go ahead and do some of the algebra here, or maybe demonstrate what I would do. You bring this over here, you're going to get -2, right? You bring this over. Let me write. I'll do the calculation. Right, so you have 30. I'm taking the tangent of it and multiplying it by 20, and this ends up being 11.55. You could even write it under there, 11.55. Bring that over to the side here. This is going to be negative over here, right? So equals, all right, so we have negative right here. So we're about to see there's a bunch of, all the negatives are going to go away. So we can multiply 32.2 times 1/2 times 20 squared. So we'll go 32.2, dividing it by 2, multiply it by 20 squared. Boom. I get 6,400. And then I could even divide that by the cosine squared of 30. So I'll take cosine squared, boom. That actually comes out to 0.75, interesting. And I divide by that. So now I have like 8,587 divided by VO squared. So wrangle around there. All those things become positive right here. So that's like 13,11,5. So now I just divide this by 13 plus. There you go. VO squared is equal to 8,587 divided by 13.55. I take the square root of both of those. VO, I think I'm okay. Yeah, hit me there. Boom. And I get 25.18 feet per second, which is the answer, right? That's what we said the answer was going to be. Where is the cursor? There we go. Yay, 25.2. Whoopee! Yay for getting the right answer. A lot more satisfying when you get the right answer.
Hey, sir. Sorry, I joined with my phone because the mic in my laptop is not working.
Okay, great.
For this problem, are you gonna send us like the solution, how you solve the problem and everything?
Yeah, I'm gonna turn it on tomorrow.
Okay. For that problem, exactly, we don't have it in the exam prep sheet, but when I saw it, it was it looked good because of that. I told you to solve it.
Oh, this one was in the exam prep, right?
No, it's not. I didn't find it there.
It isn't?
Mm-hmm.
Huh. Well, look how slow my computer's going right there. This guy right here? Should be there. Why are you so slow? Right there, right?
For us, the exam prep, I find when I went to exam prep, I find like, oh, okay. I was looking in the second slide. There is another one, like it has other problems. Sorry about that.
Okay, no problem. But yeah, this is the place to go to, and this one will be turned on. No, this one that's just the projectile motion problems. Yeah.
Yeah, I was solving that problem.
Yeah, these are just extra problems. I could do these. I could work on these too.
Okay. For this
I just didn't like. I just didn't post. I never bothered writing all the solutions out to all of these, so I never bothered posting them.
Okay.
But I figure they're just you know, these are some of these are really challenging. I would never give these a couple of these on an exam. Like I would never give this problem right here, the one at the bottom. I would never give this problem, but it's kind of an interesting problem to work on. But it is.
I tried to solve them, but I was a little bit stuck.
Which one is that? The first one?
For the first one, I tried to calculate in the XY direction. Like the first one, I can like solve it. I'm talking about the last two.
Oh, these last two ones?
Yeah.
Yeah, there's like a trick that you got to do on this. It's not. It's not. I don't know. Everything you could call anything a trick that you don't know how to do, right? And then as soon as somebody shows you how to do it, it's like, oh, okay, well that makes sense. But let me see if I can find.
Like for the second problem in the exam prep, it's similar to the first problem.
You mean this one, or do you mean
that one?
Yeah. This is very, very similar to this one. It's basically the same problem.
We use the V in place of we have like the V in place of the, what do you call it, the X. So yeah.
Yeah, you basically just go through the same routine.
Yeah.
Excuse me, sorry. What would you like to do next?
Like for the third one of the plane, like when I looked at it, like how do you call it? We use like g as acceleration in y direction, and see the, and we have the distance.
Yeah.
Uh,
Well, we just want to find the distance,
No, we
right?
find the distance. We have the speed, and we have the acceleration, and
Yep.
we have like the how do you, altitude, and we find the, I think how do you call it? We calculate the x for we have the acceleration, and we have everything, and we can calculate the same thing we did it in the first problems, like x and y, and we mix them together to find the distance.
Yeah, that's essentially most of the time what's going on, you know. But there is a shortcut that you can do in this particular problem. It doesn't always work this way, but there you can be on the lookout that you could solve for the time. Like you can find what time it's going to hit the ground.
Oh, I didn't solve at all at the time here.
Yeah, if you just solve for the time, and then in the x direction, you can figure out what the distance is going to be.
If we solve in the time here, like we put t0 when it starts, and the final. Okay. Can you show us like real fast? How did you?
Okay, I'll show you. Sure. Moving kind of slow this morning. There we go. All right. So in this, I guess this is actually problem like 3, isn't it? I don't know how we numbered it.
Yeah, it's problem 3.
Right. So this thing's moving with this velocity that we know, which is 315 kilometers per hour. We'd like to turn that into meters per second. Would be a better thing for us. So we take 1,000 meters per kilometer divided by 3,600 seconds per hour, right? And we end up finding that this is like 87.5. Actually, I want to get the better number. I don't like that. I need have another sig fig. I'm all about at least 4 sig figs for calculations there. Yeah, it is 86. Okay, 87.50. Okay, meters per second. We know that the acceleration in the x direction is 0, right? So it's going to obey that constant velocity. Whoop. I have to put plus v0 x times t. But this right here is actually, this v0 is actually all in the x direction. What are you doing here? Go away. Stop. I hate things that want to update themselves. Go away. Well, we could do the same kind of thing that we did before. We could establish that this is where xo is going to be. We'll set xo equal to 0. Sorry, my camera keeps doing that. All right. And so this distance right here, this will be y0, right? And they told us that it was 80 meters, right?
Yes.
So y0 is 80 meters. So if we do the time right here, we just multiply it by that velocity, we'd be able to find this distance, right?
So we find the time by using the y.
Yeah, so we use y is equal to y0 plus velocity y minus 1/2 g t squared, right?
Yes.
Fortunately for us, this is going to be the 0, right? Because it's going to hit the ground.
Oh yes, yeah.
I decided so 0 is equal to 80 plus, and the initial velocity in the y is 0, right? So we don't have to worry about the time then. Minus 1/2, I go 9.81 t squared.
Yeah.
So we could just solve for time right here. We could say 80 times 2 divided by 9.81.
Yes.
And take the square root, and we say that it's going to hit the ground at 4.0386 seconds. So that distance, which is d, I should have written d, and we started at 0, so it's going to be plus 87.50 times 4.0386.
Okay.
Right? So we're saying that's 353.4 meters.
Yeah. For me, I solve it the long way.
Yeah, I understand it, but some of solving these is maybe going through. You could go through every single scenario that possibly exists, or you can, hopefully, as you're working through, that you can start to get better and better at, getting that aha muscle working, right? That where you go,
Yeah.
oh, I get it. I see what I could do here, and then it becomes a simpler problem once you really, feel comfortable with practicing solving these kinds of problems.
Okay.
Got other suggestions? I see Jacob's there, right? Jacob's, you with us?
I'm here, yeah.
Do you have any requests?
No, I'm just watching and then just taking notes myself. Just, yeah.
Well, I mean,
Like,
I think you get a lot more out of it if if you ask a question that's on
I
your
don't know what to
mind.
ask at the moment. I'm haven't decided what to ask yet.
Okay.
Yep.
Not trying to put pressure on you. I'm just trying to suggest that I think you'll get more out from asking something. So if you can if you do think of a question, make sure don't hesitate to ask.
I will.
for me, like for the fourth problem, as we know, we solved problems like that. They told us to find how do you call it? Here I did the derivation of A and everything, and to find the V.
Yeah.
After
We need to integrate, right?
Wait, integrate. Yeah, integration.
So we see that acceleration is a function of time.
Yeah.
And we want to be able to find velocity. So, we work this, and use our calculus skills.
Here it was like simple, how do you call it, integration problems. It wasn't a problem, and you don't need to do the fourth problem. I was just talking about it the thing I was thinking about.
Okay.
And
I can find another problem along those lines if you'd like.
Yes, please.
Okay. Well, here is our book. Let's see if I can get it to drag over here. Boom. Wake up, book. Okay. And we can just do some of the first problems that we have right here. Let's see if we can find one that's kind of an integration one. There's positions. These are all derivative ones, I think. And okay, so here you go. This is probably a tough one. Let me close up this bar and close up this so it becomes bigger. Many car companies are performing research on the collision avoidance. There's interesting, right? A small prototype applies engine braking that decelerates the vehicle according to the relationship A is equal to negative k squared to t, where a and t are expressed in meters per second squared and seconds respectively. The vehicle is traveling at 20 meters per second when its radar sensors detect a stationary obstacle. Knowing that it takes the prototype vehicles 4 seconds to stop, determine expressions for the velocity and position as a function of time and how far the vehicle traveled before it stopped. Okay, so for one thing we have to do that, the wrinkle they throw in here is there's an unknown k in here. So we might be, that's one of the first things that we would notice when looking at this problem and maybe get like a little nervous because we haven't had a problem exactly like that. So we have to demonstrate some of our bravery in this instance and just start proceeding as best we can with that, with sort of the optimism in mind that we're going to be able to figure out a way to solve this problem. So we write that down. A is equal to negative k square root of t. And maybe one of the first things I know that the acceleration is a function of time. Therefore, I'm probably going to use acceleration is equal dv dt, right?
Yes.
So, but also, let me see some of the other information. They tell us well, let's just write this out. Okay, so I'm going to go dv is equal to a times dt. Right? I just multiplied that and just flipped them over to the side. And I want to integrate both of these.
Okay.
And from one of them, it's going to be from VO to V, and the other is going to be from 0 to T. So I put this back into there. I'll go ahead and go V minus VO. So that's the one over on the left-hand side. This one over here, I have to do a little bit more work. I have a negative K. I know that's a constant, so I'm going to put them over here. And I have a T to the 1/2, right? dt from 0 to t. So I know if I take the integral of
3 over wait 2
okay,
over 3 t 3 over 2.
Yeah, right. So you have 2 over 3
T
3 over 2.
3 over 2, yeah.
And it goes from 0 to t, so then it just equals that, right? So we have an expression now that v is equal to VO minus k 2/3 t to the 3/2.
Yeah.
Now they tell us some awesome information. They say it takes the prototype 4 seconds to stop if it's going 20 meters per second, right? So that means that at t equals 4 seconds, v is equal to 0 when VO is equal to 20 meters per second. So that means 0 is equal to 20 minus k 2/3 4 to the 3/2. So we can find k. So we just say 20, all right, take 4 and raise it to the 3/2. And that's how I do it on my calculator. And then multiply it by 2, divide it by 3. Now we can divide 20 by that. And I get 3.75, and that's correct, yeah, 3.750, right?
Okay.
And now it says we want to find expressions now. Okay, so we want to go back to this right here. We know that this is equal to VO minus, well, I might as well multiply by 2/3 too. I should take 3.75, multiply it by 2/3, and 2 times 3 divide. Okay, so it ends up being 2.5 t to the 3/2. So there you go. This is an expression that's true generically for us. So if we want to, and I guess it's still I guess this we want to put 20 in there as well. Let's put 20 in there because that's for us. That's like that's when this k is constant, right? So I think you have to apply it to that.
So when it's 20, also we can substitute like t equal 4. Because
now we can say well, we could say that now we know this velocity. You know, now if we want to know the velocity at any particular time, we'll be able to find it under these conditions.
Oh, okay, I understand.
All right. Yeah. So now, so this is like the first thing that was asked in the problem. Let's see if I can get the thing up here. You keep seeing pictures of my forearm. Come on, get up, get up. Where are you? There you go. There it is. Let's see. So the first thing it asked for was an expression for the velocity. Oh, and they want and position as a function of time. So now we have to go. Well, velocity is equal to dx dt, right? So we could go to dx is equal to v dt, and then integrate both of them. But we could put the velocity now inside of there. So this is from x naught to x, and this is from v naught to v. No, I mean from 0 to t. Sorry, it's time that we're working on, right? Time is the variable, so it's going to be 0 to t. So we'll get x minus x0, and for this, the integral of 20 minus t 2.5 t 3/2 from 0 to t dt. So we get 20t.
Yeah.
And here we got to do that again, right? So now we have to add 1 to this. So is that going to be 5/2?
It's 4 minus 4 over minus 5 over 5. It's 1 because yeah, because it's become t to, yeah, and when we multiply minus negative 2.5 multiplied by 2 over 5, it's 1. So it's equal. (20t) and plus minus t.
Yeah, I just want to double check something right there. Yeah, so actually these actually kind of cancel each other out. 2.5 times 2 and divided by 5 ends up being 1, right? So
yeah.
Interestingly enough. And you can assume, I think, the position is starting at 0, right? We could just say that it starts at, 0 because that's where you would start measuring it, right?
Yeah.
That's totally fair. But now you're like want to find out the distance that it has traveled in 4 seconds, right? Well, if we say, we just assume that right there is 0, then we could say that 20 then when at t equals 4 seconds, right? The distance that has traveled would be that 4 minus 4 to the 5/2, and I think you see 4, 5, 2 divided, raise that becomes 32 right here. This together comes 32, and that's going to be 80. So we subtract it out, and so we end up getting 48. And these are, did they ever tell us what units? We're in meters, right?
Yeah. I think,
There you
no,
go.
I think, yeah, meters, because the velocity is meter seconds.
Yep, yep.
Yeah. That's quite good problem.
Yeah, it's a good problem though, right? Because you didn't. I mean, this is what we're trying to learn to do, is to take a problem that at first puzzles us, and use the principles that we know, and to be able to work through them. So,
Sure, like,
so it's challenging. I prefer not to try to test people's calculus skills, though, right? So
yeah.
I think that one's kind of fair because it's fairly straightforward calculus, but I don't want to get into one where people have to start like coming up, remember some more complicated integral form, right? That's not
Sure.
really what I want to.
Quite similar. I think it's quite similar to problem 5 we have in the exam prep. I think so.
Yeah, it's similar to that. My colleague Alicia Garcia, she liked writing these problems, so a lot of these are hers.
Yeah.
I do believe
this
is my problem. I think I wrote this one.
Like, sure, for this.
Yeah, so this is this is like a polar coordinates problem.
Yeah, like you told us in the class, every time when we have this kind of problem, we write like r dot, r double dot, and theta dot, theta double dot. We calculate them. After that, we start solving.
Yeah, yep.
I did like that. I could solve the problem.
Yeah, I think it's pretty straightforward there. But here was the kicker in this problem was C. Can you sketch the velocity vector?
I couldn't.
I think you could. It's at that right there is almost like a you don't even need to like do any calculus or any calculations.
Sure, like I know, like for when we do like from r to r dot or r double dot,
Yep.
we do like we know for r to do r dot, it's we do pi over 2. We take it out because when we do the normal derivation and everything.
But here, what I'm asking in part C is something that is like I wrote in really big letters on the board something you were supposed to remember, right? Velocity is always tangent to the path.
Okay. Oh yes.
So you could just sketch on this. You really could just for that particular one, it had a thing was going wee like that or whatever the hell it was. You saw that point. You could just sketch, right? It's just going to be tangent to that curve where the point is at, right? If it was over here, you could just kind of like go there. You kind of had to know that it was starting here and moving that way, but you could tell that just from the equations that when you just set t equal to 0, and you could see, well, the angle is going to be 0, so this must be where it's starting. You could also put 0 in for here, and you would see that you would get like 2.5 right there. So that's when t is equal to 0. So it's moving in this direction. So that the velocity has to be coming up that way right there.
Yeah.
I wrote that problem, and I was very proud of asking that part there.
Like I made the mistake when
it demonstrated whether you knew that fundamental thing that was really important.
Okay, like at first I did the mistake when I was derivating like the cos pi over 2t. I took only the t out. I forgot pi over 2.
Yeah.
Like we need to take everything out there, because it's not like we solve a problem in the class. It was like It was theta inside minus pi over 2. We only took the theta.
Yeah, yeah. I generally don't try to. I avoid the problems where you have to use that chain rule thing. You know,
So for us, sir, I just wanted to ask this so I understand it properly. Like, in case of problems like we have for like r is 2.5 plus sine theta like minus pi over 3. When we do the derivation, we took like the theta outside. We don't took the pi over 3.
okay, so I'm not sure where the pi over 3 came from. You're talking about you just came up with a different one, or are you talking about a
Yeah, I
particular
just came
problem?
with different one. I just came with different
Okay,
one, like
I think I understand what you're saying.
example inside my head.
Okay. I wasn't listening close enough to be able to remember what you had said, what you said the original part of the problem was.
Like I put like r is equal like 2.5 plus sine like theta minus pi over 3. And when
Okay,
you
wait,
do the
slow down, slow down,
derivation,
slow down. Say it again, say it again. R is equal to, wait, let me move my,
2.5 plus sine like theta minus like pi over 3. I think we did one similar in the class. So when we did the derivation for this one, we don't take the pi over 3 out.
yeah, that's just a constant, right? You have to remember, you know, like you need to take the derivative of the inside of this thing.
Yeah. Okay. In that case here, when we have like pi over 2t. Because of that, we take the derivative like of pi over 2.
Yeah.
Because
Yeah,
the
we say,
yeah.
So this is one that's a function of, you know, that R is a function of theta here.
Theta, yeah.
Whereas the other problem, R was a function of time.
Okay.
So it was a little easier right in there. But in both cases, we will have to, at some point, take the derivative of the stuff on the inside. Let's see where I go back to this.
Like
Yeah,
now, every time I see problem like that, I put R theta, R double theta, R dot, R double dot, and theta dot, theta double dot. After that, I find this, like I start solving problems.
Yeah, yeah. You want to go to the variables of interest is the key thing that you recognize you're going to have to do when you're here.
Yeah.
Problems the things that I don't have in these example exams that can be on our exam, just as a warning, is I don't really have coordinate transformation in some of these practice problems, because these all came from the Coast Guard Academy when I was teaching at the Coast Guard Academy. In fact, you'll see, like, this is spring of 2017, right? And I'm not sure I have the year for that, but I wasn't using the coordinate transformation back then to solve the problems. So some of the solutions won't show that, but I might ask for it on the exam to do a coordinate transformation. So just, you know, fair warning.
Like, can you like show us any problems from the book about coordinate transformation?
Okay, I'll try to find one. You know, this is a lot of times this is like what is it, live without a net? You know, I don't have a. I have to see if I can find one. Let's see. So I'm going to go to the non-rectangular section 11.5 here and look for some problems where it might be like useful to us. Okay. I don't like how they use the blue background there. All right, so here was a problem from a couple years ago. Someone picked this one as the exam problem, but it doesn't have any numbers in it. I like problems in numbers. Give me problems in numbers. We've done this. I've done this one before. Doesn't quite need a coordinate transformation, but we could do it anyway.
Okay.
Yeah, let's do it anyway. All right, so we have this plane, and it's down at the bottom of this. It's kind of taking a dive, right? But it's doing it with a curvature to it. That's like 1 mile worth of curvature. And we want to find what the recorded r dot, r double dot, and theta double dot are going to be at this instant. This one sounds like it's the same. Oh no, okay, this is like similar there. Like, okay, we could do either one of these. This is that type of problem. So let me put this over to. Let me let's see what problem number is this first. I'll just look at the problem number. All right, that's 169.
So in that case here, like we need to find the ER and the E theta.
Yeah.
Yeah, we make hours and we calculate with them.
But one of the first things we want to do though is get the I and J first, right? Of the plane.
I and J, and we find the cos and the sine of it.
Yeah.
Okay.
It's a similar routine we've done before. All right. So
sorry,
let me see if
I'm talking a lot, sir, because
no, not at all, man. I prefer that to dead silence. I gotta tell you, I hated doing this remote teaching stuff. I just can't stand the loneliness of it. It doesn't seem that I can't get students to interact at all. So this is good for me. All right. So at this instant, the plane is kind of horizontal.
Yes.
I didn't do a very good airplane drawing. You'll have to forgive me here.
It's clear.
Here. And let's see. We know this. So we have to have. We know this is r and this is theta. All right. So this is how theta is being measured right there. And this was 2,400 feet, and this is 1,800 feet. That's pretty low, actually, right? And I guess this is
for an airplane. Yeah, I think so.
1 mile, which we know is 5,280 feet. Okay, and so the plane's velocity is 315 miles per hour. So let's just go 52803600. We've done that a bunch of times, so we're kind of used to it. 5280 times 3600, boom, and we should get 462 feet per second, if I did that right. Sure. And let's see what this. We can figure out. We know that we're going to go the variables of interest, right? Are the things that we're going to want to find. So we can find r right away. Square root of 1,800 squared plus 2,400 squared. That ends up being 3,000. I guess this is a 3, 4, 5 triangle of some sort, right?
Yeah, so it's like 3,000. Yeah.
Yeah. And theta, we could take just rise over run. So take the inverse tan of 1,800 over 2,400, but we know it's a 3, 4, 5, so it's going to turn out to be that very
56 yeah.
Yeah, we get that one a lot. I wish I'd get rid of this little square. Why are you there? Getting rid of that stupid square. All right. So we actually have 2 of these already. That's good news. And so we have the velocity is 462.0 I. The acceleration now, though, let's see. It's speeding up. Okay, one of the things it was telling us is it's speeding up, which is another way of saying dv dt is going to be 10 feet per second squared. But that's not the only acceleration it's experiencing. It's also in a loop, right? It's also coming down right there. So this right here is going to be its tangential. It's also going to be equal to, it's also going to be equal to its I. You're right. It's also this acceleration right here, right?
Yes.
It's also its x, because the tangential is aligned with the x. But also now at this point, there's also going to be one coming upwards, right? There's going to be a normal acceleration, and that one's aligned with the y. So we can get the acceleration. The normal one is going to be the acceleration in the y direction. Is going to be v squared over rho. So that's going to be equal to 462.0 squared divided by 1 mile, right? Or 5,200.
The curvature.
Yeah. So 462.5280, and we get that it's going to be 40.43 feet per second squared. So now the acceleration we know is 10 I plus 40.43 J feet per second squared.
Sometimes I make a mistake. I put A and it's V squared over R sometimes, because I'm used to that.
Oh, that's fine. No, I mean, you know, it's just as well to write R instead. I don't know why we write rho, but it's just somebody was maybe just trying to be in some books you'll see R. People, I mean, I don't know. It's just this. It's just the thing of the authors of this book are used to doing. There are a lot of books
I remember it that way.
Yeah. Whatever it takes. They mean the same thing. Okay. I don't care. It's all, you know. I don't worry about that kind of thing too much. But anyway, okay, so we have it in I and J. So obviously the best thing for us to do is do a coordinate transformation. So looking at this carefully, we can see that the ER is going to be in that direction, right?
Yes.
E theta is going counterclockwise, so that by its definition is this one right here, right? E theta. And we have I, and we have J. No, what did I just do? Oh, geez. I and J. What's going on? So here's that angle, which we know is the same one as this.
36, yeah.
And if we needed it, we could say that and that too. But we set up our coordinate transformation array. Here's my I and J, my ER and E theta. They forgot their hats. And so we start out with our ER. We see that it's cosine. ER looks like it's going to be sine. And then we go E theta. Oh, looks like it's negative sine. And it looks like it's going to be cosine.
Yeah.
So for the velocity, we say, well, okay, now we want the velocity in terms of this. So this is only I, so we only have to go down this column. So we go 462.0
cosine
times cosine, and we'll go ahead and put the number in, 36.87
plus
ER, right? And then plus 462.0 times negative sine E theta.
Yes.
So this ends up equaling 36.87, and of course this cosine, this is going to be 0.8. Multiply it by it, and you get 369.6, and it's positive. And we know that this right here is R dot.
And it's like negative 277.2, the second one.
What was the number?
Negative 277.2.
Yep. And we know that this guy is r theta.
Oh yeah, from the equation.
Yeah, so we can solve for theta by taking this and dividing it by r, or
And you have
negative
R.
277.2, and our r was our 3,000, right?
Yes.
So 277.2 and 3,000, and you get I don't know if I did that right. 277.2 and 3,000. Yeah, I guess so. Okay. 0.09240, and these are radians per second, right? So now we have our you know, we have this, we have this, we have this, and we have this. So we only have two left. We had to take that acceleration and turn it into, so 10. And if we're feeling comfortable with it, we could do this, you know, and it kind of collect the ERs together, right? So we go 10 times that cosine of 36.87, and then we're going to plus 40.43.
Negative sign 36.8.
I think we're going to go this guy right here, though, because I'm taking this one and multiplying it by here, right?
Okay.
And I'm kind of crossing them there because I just want to only do the ERs.
Okay, you do the AR alone after the T total.
Yeah, I mean, I don't know if it's saving us any real time, but maybe an itty bitty amount of time. 10 times, now I go 10 times the negative sign of, 36.87. No, it's just not a bracket, but there. And then plus 40.43 times cosine. So we end up getting, 10, 36.87, but I know that should be 0.8, so just multiply it, so that's just going to be 8. And then 40.43 and 36.8, times. And we're going to add them together. So 32.26. 32.26, did I get the same thing? Yeah. ER plus 10 times my 36.87 sine times, but make sure he's negative, and 40.43, 36.87, take the cosine, boom, and then add them. It's still positive, 26.34 E theta, if I did the math right. Let's see. Yes, okay. So we know that this right here is going to be r double dot minus r theta dot squared.
Yeah.
Right. So we could find our r double dot by taking 32.26 and adding the 3,000 times this theta dot up here squared, 0.09240 squared, and I'll just write it underneath it. So 0.0924 square 3,000, and we're going to add 32.26 to it, and I should get my 57.87, and these should be feet per second squared. And then the last one I need to do is I got to get this guy right here. And I know he's going to be r times theta double dot. I can't write the thing in there, right? I didn't leave myself enough room. Plus 2 r dot theta dot. And we remember, we think of this as the Coriolis acceleration, which is related to merry-go-rounds. Okay, so we'll take, I'll just write it out, 3,000 theta double dot plus 2 times r dot, which we got up above somewhere, right? Up here, right?
Over there, yeah. 369.
369.6. And then theta dot, which is right here, right? 0.09240. And that's going to equal to 26.34. So yeah, we can get a third, so we get 26.34 and 0.0924 times 369.6 times 2, and we're going to subtract that from that, and so we get a negative value and divide by 3,000, and so we end up getting a negative. I'll write it out here. I think it's 1399, and that should be radians per second squared. So we think back about what is I got negative. Well, no, they're saying it shouldn't be negative. Whoa. Is that true? Why? I didn't find it to be negative. Why? What did I do wrong? I think it should be okay. Oh, maybe I was supposed to get theta dot was supposed to be negative. Yeah. Whoops. Up here. Shoot. See that? Made a mistake. Okay. That's supposed to be negative, so that's negative right there. So when this comes over to there, they're going to add together. Oops. 0.0924. 369.6 times 2 times, so we're going to add it to 26.34 and then divide by 3,000. So we get a positive 0.03155 radians per second squared. All right. So, and this actually makes a lot more, this makes sense. So it's, what's a really good idea is to go back to the original problem and look what you have, right? So r dot means that the distance is increasing, right? As which makes sense, right? That the distance from here to there, it's going to get longer. And we also see that it's rotating, but of course that means, yeah, it's rotating this way, right? Because it's going negative because positive was that way. So it's obviously rotating. But the amount that it's rotating is positive. I mean, the rate at which its rotation is changing. So it might be going this way, but it's getting slower and slower, right?
Yes.
So that makes sense. It also makes sense that it's the rate of the r double dot. This right here is getting longer, so that's why it's like a fishing line, right? Where you can think of that distance as being, whereas this is the pivoting of the stool, if you will. But of course, this is on the vertical plane instead of horizontal plane.
Okay.
That's a pretty good problem because it has the coordinate transformation in it. It's a little long.
Are you gonna send us this problem to tomorrow?
Am I gonna send you this problem tomorrow?
Yeah. Are you gonna send it with the other problems, like?
Yeah. I'm gonna send the solutions.
Okay.
I'll
Yeah.
activate the things so that you could see the solutions. But I'd rather
Okay.
I'd rather you work all the problems yourself.
No,
You
I'm
know.
working the problems. Like
Yeah.
tomorrow, I'm just like this problem. We don't have it in the sheet. It's in the book.
No.
So because
But I
of
got
that, I
to
wanted to have it.
I really want you to try this because this is really how I like made a transition from being just an okay student to being a really good student, was when
Okay.
I started going to the back of the book here and looking at, let's see, go into right here. We're in chapter 11, right? And just picking out a problem. Just going, okay, oh, look, there's the solution to problem 11-129. Well, that's what the answer is, right? Just look at the answer, and I don't even know what this problem is, all right? So I'm taking a risk here. But 11-129, I just picked it out of the hat. I swear to you, 5.96 meters per second, and then there's the angle right there. But I know it's kind of like in the area of things I should know how to do, right?
Yes.
So go to that problem, and it's going to be somewhere down here. I think I could have made a big mistake. Oh, there's one right there. All right. So this is the problem, right? We have, during a rainstorm, paths of a raindrop appear to form an angle of 30 degrees with the vertical to be detected to the left when observed from the side window of a train moving at 15 kilometers per hour. So V is 15 kilometers per hour, right? And a short time later, after the speed of the train has increased to, all right, so this is going to be 1, let me go V2, is going to be 24 kilometers per hour. The angle between the vertical path and the passenger appears to be 45. So there's the angle is 30 degrees. At here, the angle is 45 degrees. Angle between the vertical passenger's head. If the train were stopped, at what angle and with what velocity would the drops be observed to fall? Boy, that is some serious. That's a hard problem to try to work through. But let's try to see if we can try to figure out what's going on here. So this is a relative motion problem, right?
Yeah.
So that's one thing that we know. And but we have to I'm trying to think, is there any acceleration as part of this? I don't think so, but it was weird how they gave us two different angles at two different speeds. Okay, so what we do as part of this, like, so I'm writing this stuff down right here, and I'm trying to think, okay, so like, let's just take a look and draw out the window, and we have like a raindrop is appearing to come down this way right here. And I have to look at the words too. Is it, are they saying with the vertical, right? It is formed with an angle of 30 degrees with the vertical. Okay, so they mean from here. That's the raindrop, right? So it's going at one speed. It looks like it's going at 30 degrees. At another speed, it looks like, and I'm exaggerating right here, that it's going at 45 degrees, right? We'll say this is 30 degrees on that first one right there. So what we really have to say is that we have a train velocity that's coming this way right here, but this is like the direction with respect to the train, right? So we can almost think of this as being V is rain with respect to train, where this is the V of the train. So I'm trying to think of what their logic is right here in the problem. So I'm cheating just a second. But if I had enough time, I would be like messing around with this. Yeah, this is a hard problem. I picked a really difficult problem. But we can rationalize our way out of this. Oh man, I think I'm going to cause all kinds of problems if I try to explain.
It's a little bit messy because we don't have like the initial, for us, like we used to have at least like we know how do you call it, the initial point where it started and how much it turned around, so we can calculate.
Yeah, this is really playing a game with a little bit of geometry right here. And actually they gave me two different ways to do it. I prefer what they have with this other way right here. All right, so what they've told us essentially is that, and we know the velocity of the train, and we know the angles that can be made of the thing, right? So we have two equations, and we can get two unknowns right here. So like once again, this is the velocity of the rain with respect to the train. So if we want to find the velocity of the rain, right? It could be equal to the velocity of the train plus the velocity of the rain with respect to the train, right here. And these are all vectors. And we know this. We don't know this, but we know, and we don't know the magnitude of this, but we do know the direction of it. So what we can say to be able to solve the thing is the velocity of the rain at this first condition right here is going to be 1 second here. I guess I'll keep it as this. I'll go 15, right? I plus and so this the velocity of the rain is going to be something I plus something. Let me go this way right here. Oh, I'm sorry. Velocity of the rain is going to be equal to velocity of the rain. Oh, let me try it another way. Velocity of the rain with respect to the train is going to be equal to the velocity of the rain with respect to the train times the. I got to be careful here. Do I want to do that?
Yeah. They're like, they didn't give us a lot of information how to do it at start.
Yeah, but it's still this. I was trying to demonstrate the thought process, or the thing that I think that is the way that I did it in college, right, was to take problems that were out of the back of the book and then force myself to try to find what that solution was going to be. And it's really hard to do, but by then doing it, you're really pushing yourself. But I'm not gonna go further with the problem. I could just show you what the solution was going to be. I'll write it up later and post it. So yeah, let's do some more problems.
Like
do you have a type of problem that you like to?
Like problem 8. If we go problem 8, we have like it's quite how do you call it? For the problems before, we didn't have like the acceleration and everything, but here we have them.
Well, let's see here. The robot arm moves, so the particle travels in a circle about right here, which about point B, and that point B is not moving. Okay. knowing that p starts from rest and its speed increases at a constant rate of 10 millimeters per second squared, determine the magnitude of the acceleration when t equals 4 seconds and the time for the magnitude of the acceleration to be 80 millimeters per second. Yeah, so this is definitely my former colleague Alicia Garcia's type of problem. She likes this kind of thing. So we have that arm, and he's moving, right? And he's moving, and they tell you he's moving in a circle, right? And it says that the speed is increasing. Is it going? I guess I don't know if it matters whether it's going clockwise or counterclockwise. Moves it travel in a circle about p, which is not moving, knowing that it starts from rest and its speed increases at a constant right here. So it's not telling you what direction it's going, but I'm going to go ahead and assume it's going in that direction right there. So this is going to be the v, and so the acceleration in the tangential is a constant. So that's going to be 10 millimeters per second squared, right? And it starts from rest, right? So it's going like velocity this plus acceleration times time, and that'll be the tangential acceleration, right? So we can find what the velocity is because it starts from rest. At t equals 4 seconds right here, we could find that the velocity is going to be 10 times 4, so it's just going to be 40 millimeters per second, right?
Yes.
And so, how come I said it was?
They told us the magnetic acceleration.
Oh, I see. Okay, I see. I got it. So we can get the acceleration in the normal direction.
V squared over r.
Yeah.
Yeah.
You could do it. But it doesn't matter. And the thing is what? 80. We'll keep it as millimeters. That'll make life easier.
Yeah.
So 40 squared divided by 800, we end up with 2. Millimeters per second squared. So we want to find the magnitude of the acceleration. That's just going to be AT squared and AN squared. Or 10 squared plus 2 squared.
$10.19.
Yeah. And then they also were asking about it going backwards, right? So they say at what time, when is the magnitude equal to 80?
At what time?
All right, so what we could do is we could work backwards to the thing, is we could say, okay, we know that AT is always equal to 10 millimeters per second squared. We would like to get this in terms of time, right? So if we go back to this original thing right here, we could also have said that this is going to be equal to 10t right there, right?
That's in the I direction.
Yeah, well, it's just in the tangential direction.
Yeah.
Because velocity is always tangent to the path. We haven't done it. We don't need to do a coordinate transformation here. We don't actually know what the position of the arm is going to be. We only know that it's moving kind of in a circular path right here.
Okay.
It's moving in a circular path because it's moving about this fixed point. Even though they tried to make it look complicated with the thing, it's really just a circular motion onto it. And so we know that this is v squared over here. So we could take the 10t squared over whatever it's called, what is it, 800. And we could do the same thing right here. We just say 80 is equal to the square of 10 squared plus 10t squared over 800 squared, right?
Okay.
And we can solve for t. So I just make 80 squared. So 6400 is going to be equal to, and then we got, this is going to be 100, and let's see, take it, so this is going to be 10 squared divided by 800 and then that whole thing squared. So it's going to be 0.01563 times t fourthed. So could subtract out, I think I'm going to get it right. Subtract that out. Divide that through. And then I got to take it to the 1/4 power, right? Yeah. T is equal to 25.20 seconds. Now, I don't necessarily think of it in these ways, but sometimes when writing exams, some of the mindset is to take a simple problem that's fundamentally simple and work backwards and kind of write it in such a way that it makes it difficult for a student to, you know, you're not trying to trick a student necessarily, but you're trying to make it kind of disguised as something that was like much more complicated than it really is.
Okay.
I think that could be kind of unfair to a student to do that, but that's kind of what was going on here a little bit, right? That you were like, well, that's a pretty simple problem. But when you look at the problem, you're kind of like, oh, you're muddling up the different concepts, and it kind of looks like it could be, oh, do I need to do a coordinate transformation and that kind of thing, or do I,
Yes.
do I need to use polar coordinates? In fact, I might have accidentally wrote, I don't think polar coordinates is really kind of correct in this. I don't think I think I should change that. I shouldn't even call it polar coordinate because this is really tangential and, you know, normal and tangential.
When I saw polar coordinate like in the problem, I said, why didn't we use them? Like, yeah.
Yeah. I think I mislabeled this one, to tell you the truth. I should go back and fix that.
Sir, thank you very much for the lesson. I need to go now.
Okay, yeah, I need to go too. Is anybody else with us? It was just you and me,
Jacob.
man. You're getting like one-on-one. No, Jacob's been here.
Oh, yeah. So like for this kind of problem, like 12, we have one of it, like the train and the car. We solve it in the class, similar to it. So.
It's a good idea to do it's a good idea to get some relative motion practice, because I think that came on a homework where there was only 2 problems, and you know, the one that I started doing, maybe you know, embarrassingly, I was like looking in and going, that's way too complicated. This is a relative motion problem, and it's a good. I don't think we've done enough. I wish we had done more where we do triangles, right? To do vector triangles, because they're really important. This is a terrible example to do vector triangles. This is a hard relative motion problem, just because it's kind of like off the beaten path. They're doing a game here where they're telling you two separate situations, and then you're going to be able, based on having two sets of equations, you're going to be able to solve for the unknowns. So it's I think I'm going to like organize my thoughts for this one, but I would encourage you to try some other relative motion problems. And
I will try to finish all the problems that we have in prep exam. Like I will try to solve the problems. We have all of them there.
It's a good idea, because you know, when I taught statics last semester, or yeah, in the previous 2 semesters, not teaching this semester, but I started using the problems out of the book because I hadn't taught the class before. I went ahead and used these, but I've actually been, you know, in dynamics purposefully don't use the sample problems in the book so that you will have them, right? So that you have that as a resource. So maybe I should emphasize that more in class, or talk about it more in class. You should really be looking at these sample problems as additional problems. And if you're stuck on like a particular thing, or you want to get stronger, go to the problem and just cover up the solution and try it yourself. Try it, because you do have, you know, these are fully worked out problems, and so you could be testing yourself. And you know, this book is a really well-made book by really smart guys, and this is the 12th edition. They kept making it better every time. Supposedly, right? This is the way I think of it when looking at problems in any book. Any of these problems you should be able to do if you can do these sample problems, right? That's the idea that the authors had in mind. So they've given you these sample problems, and between what they've written in the text right here and your experience from these sample problems, you should be able to do any of the problems that they've put in here. That isn't always true, but that's the idea. So you got to think of it in those terms when you're trying to like test yourself and prepare, is, can I do these sample problems? So use these also as your exam prep, right? Cover up the solution, go to the blank piece of paper, and just try to work out the thing. And you have the solutions right here to look at. So those are additional problems for you to look. I really think they're a good idea.
Thank you very much, sir.
You're welcome.
Yeah. Have a good day, sir.
You too.
Yeah. And have a good concert.
Jacob, do you have any questions? All right, well, I'm going to call it then. Have a good weekend, everybody. I hope there's some amount of helpful, if anybody's been going to watch the video, maybe this will be some helpful stuff. So we're done.